Today, we're digging into a visitor from way, way beyond our solar system. It's a comet, sure, but it's carrying some seriously strange chemical secrets. So let's get into it and unravel the mystery of Comet 3I/Atlas. Okay, let's start with a pretty weird scenario. Picture this. You open your freezer and you find a pizza that is impossibly cold. I mean, way, way colder than the freezer itself is even set to. Your first question isn't going to be what's for dinner. It's going to be, where on earth did this come from? Well, believe it or not, astronomers recently faced that exact same kind of cosmic puzzle. And the source of that whole puzzle? It's this interstellar comet, 3I/Atlas. We're going to go under the hood of this thing to see how a very special kind of water, locked deep in its ice, is acting like a tiny time capsule, telling us a wild story from a star system light years away. To crack this case, we've got to become chemical detectives. We're on the hunt for clues that are hidden deep inside the comet's ice, clues we can think of as its unique molecular fingerprints. So, our whole investigation really comes down to comparing two types of water molecules. You've got your standard, good old H2O on one side, the water we all know and love. But our real molecule of interest, our special detective molecule, is this other thing called HDO, or semi-heavy water. So, what's the deal with semi-heavy? Well, it's all about one special ingredient, deuterium. You can just think of deuterium as a heavier version of a regular hydrogen atom. It's that single D that gets swapped into the H2O formula that changes everything and gives us the critical clue we're looking for. And right here, this is the key to the entire investigation. The ratio, how much HDO there is compared to regular H2O, it acts just like a cosmic thermometer. It can tell us the exact temperature of the place where that comet was born billions of years ago. Now, what's so cool about this is how clear the principle is. In a relatively warm stellar nursery, like the one our own solar system grew up in, you end up with a pretty low amount of HDO. But if you go to an extremely cold, lonely corner of the galaxy, the ice that forms there captures a much higher amount of that heavy HDO. But wait, how does this chemical memory actually get locked into the ice in the first place? Well, the answer lies in a process we can think of as the stickiness of space. The science behind all this is a process called fractionation. Now, I know it's a bit of a mouthful, but the idea is actually pretty simple. It just means that molecules behave and react differently depending on how cold their environment is. And when we say cold, we are talking about temperatures that are almost impossible to imagine. The deep space where these comets form can get down to around -400 degrees Fahrenheit. It's in that insane cold that fractionation really kicks into high gear. Okay, so here's how it works. It really breaks down into 3 simple steps. First, you start in that extreme, bone-chilling cold. Second, at those low temperatures, deuterium becomes chemically stickier than normal hydrogen. And so third, because it's stickier, more of it gets grabbed and captured into the ice as it forms, which means you end up with more HDO. Simple as that? So the big question, when scientists finally pointed their telescopes at Comet 3I/Atlas and analyzed its water, what did they find? The results were pretty striking. They found a ton of heavy water. The ratio of HDO to H2O was way, way higher than anything we typically see in our own solar system. And based on everything we just talked about, that super high ratio can only mean one thing. This comet wasn't born in a warm, busy stellar nursery like ours was. Nope. It formed in a frigid, lonely, isolated corner of its home galaxy. It is the frozen pizza from a much, much colder freezer. Okay, so it's a cold rock from a strange place. Cool story. But why does this actually matter to us? Well, this little discovery gives us a sneak peek at the blueprints of entirely new worlds. So yeah, why is this so important? It really boils down to 3 big things. First, it proves that not all solar systems are built from the same blueprint. Some form in very different environments. Second, it helps us trace the origin of Earth's own water. Did it come from comets just like this one? And finally, this kind of research pushes our technology forward, using incredible instruments like the ALMA telescope to detect these specific molecules from light years away. When you really think about it, Comet 3I/Atlas is so much more than just a passing chunk of ice and rock. It's a messenger from a world we can never, ever visit, and it's carrying the story of its birth written in the language of chemistry. It tells a truly heavy history. So,
Next time you pour yourself a glass of water, just pause for a second and think about it. There's a real chance that some of the very molecules you're about to drink didn't form with our sun, but actually started their journey in a cold, distant star system billions of years ago and have a very, very hazy history indeed.